তাহলে এখন যেটা করবো সেটা হচ্ছে okay. So backbonding and its influence on dipole moment or structure, these things we are going to discuss today. Okay. So a very typical example that we are going to discuss is structure of NSI Me3 whole thrice. Now, this is very much similar to the very basic molecule ammonia. So one should have expected it to have a pyramidal structure just like ammonia. Okay. Hmm. This was expected. Okay. So what we are calling this as pyramidal, right? But in reality, the structure is actually a trigonal planar structure. Yeah. So this lone pair, because of which this was a pyramidal structure, if this lone pair gets donated, okay, donated where? So this lone pair is present in the p orbital, or let's say in the sp3 lobe, isn't it? Hmm. The lone pair is in the sp3. Okay. But now, if you imagine that silicon, it is belonging to the third group or third periods rather. So এখানে তাহলে d orbitals থাকবে, accessible d orbitals আছে। তো সিলিকনে যেহেতু এরকম accessible d orbitals আছে, হচ্ছেটা কি যে এই লোন পেয়ার গুলো এই d orbitals গুলোর মধ্যে ডিস্ট্রিবিউট হতে থাকে, they are getting delocalized, ঠিক আছে? And because of this delocalization, now the lone pair is no longer located on nitrogen, it is delocalized. So no, you have to think in this way. Now the lone pair is not there. So if there are three bonds and the lone pair is not there, then what is the expected structure? Obviously trigonal planar. That means we can think of that this lone pair is getting delocalized to silicon. There are three silicons, each one of them having accessible d orbitals, in which the lone pair that was present in the sp3 orbital of nitrogen, it gets delocalized. Okay. Localized means it is in one place. Delocalized means it is distributed. So now, ideally, if this was the structure, then we would have said that the dipole moment of this molecule would have been non-zero. But now, in reality, This is the actual structure, which is, as we are saying, it is trigonal planar. And so we would expect the dipole moment of this molecule to be 0. Say yes or no. এই ব্যাপারটা বোঝা গেছে? বলো। Okay. Am I clear, Anshu? Okay. So never expect these type of questions to be asked in your school exams. This will only be asked in your competitive exams. Okay. In a very similar manner. Structure of OSI Me3 whole twice. So this is very much similar to water. Expected structure would have been just like water, that is bent structure, and one would have thought that in space the OSI bonds will be oriented in the following manner, and the lone pair of electrons will be like this. Now again think of a situation in which the lone pair of electrons present in the sp3 orbital of oxygen, if they were to be delocalized to the available d orbitals of silicon. So whenever we are saying available d orbitals, always think in periodic table it has to be an element belonging to periods starting from 3 or above 3, but never can be possible for n equal to 1 period or n equal to 2 period. Okay. In those cases, the elements may be having d orbitals, but they are energetically not accessible. Okay, that is the current understanding. So if this is delocalized, now we can think of a situation where there is a O and no lone pair means two bonds, and two bonds would like to be 180 degree apart. Yes, that is Vsepr theory. Again, you can think of that this SiO bonds would be having some amount of more than single bond character, right? It is not single bond character, it is more than single bond character. We can think, but we cannot conclude that way. We cannot say two, because it is partial type of donation, right? Not complete donation. So here also we are saying mu is equal to 0. Okay, and the bond angle now, because of this fact, this back bonding, it is changing to 180, and not typically as one would have expected for a water which is 104. So this is the correct structure and that is the expected structure, but this does not happen in reality. Achha. So again, mu over here would have been non-zero. So now you can think that back bonding can affect not only the structure but also the dipole moment of a molecule. Again, let us think of a molecule, or rather compare BF3 and BF4 minus. Okay, which has longer BF bonds. Hmm? Now, when we want to answer these type of questions, we first draw the structure. Okay. So out here, let us think of that. Wait. For some reason, it is not responding. No, no, I understand, but I'm trying to record, right? So, hmm. So we have B, and there is F, F, and F. This is the most contributing structure. We have studied this already. Now, if you notice that fluorine will be having lone pairs over it, and the B is having a empty p orbital, and next we can think of that these lone pairs get donated to the boron, and we can think of these type of resonating structures in which the B is having the delta minus negative charge and fluorine is having delta positive charge. Similarly, we can draw further a few more resonating structures. This is plus and that is minus. We can have another one, which I am not showing. But what can be understood from here is that the BF bond are getting some amount of more than one bond order, okay, because of these structures. They might be less contributing, energetically less stable, but still there is some amount of backbonding happening from the fluorine to the boron. Now, if you were to compare this structure with another structure in which we have the BF bonds, now out here we can see that the boron is having 8 electrons in its outermost shell and no further resonance or backbonding is possible over here. So these BF bonds are not having any double bond character or more than a single bond character. So we will say these bonds which are having a true single bond between a B and F, this will be having a longer BF bond than the BF3. Okay, so we will say BF4 minus has longer BF bonds. Now, again, one can ask a very similar question based on the same principle, and that is the Lewis acidity order. Hmm. Ah. ভাবতে পারো, but again it is using the same fact, right? নর্মালি প্রশ্নটা দেখলে মনে হতে পারে যে ইট ইজ ডিপেন্ডেন্ট অন দি ইলেকট্রোনেগেটিভিটি অফ দি সাবস্টিটুয়েন্ট অ্যাটম, মানে মোর the electronegativity of the halogen, more will be the acidity order, because eventually what is happening over here, this p the হ্যাঁ, তো লুইস অ্যাসিডিটিটা মানে কি, একটা এমটি অরবিটাল আছে and that empty orbital is accepting lone pair of electron. Lewis acidity মানে a compound that is having empty orbitals in which it can accept lone pair of electrons. So it is all about the acceptability of the atom for a lone pair. Now, if you're already thinking that F is pulling electrons like this because of higher electronegativity, so more it pulls, more should be the ability to hold the electron into this empty orbital. That is fine, that is a good logic, but what is happening over here is something else. Now, if you compare BF3, in which B and F both belong to the period 2, with BCl3, in which B and Cl belong to period 2 and 3 respectively, and now you're thinking that where this backbonding will be better. So yes, so from 2p lone pair to 2p empty orbital will be better than from a 3p lone pair to a 2p orbital, because the energy gap is more. Understood? So donation from 2p to 3p to 2p will be less favorable than the donation of from 2p to 2p. So where donation is better because of less energy gap, its ability to accept electrons from outside will be less. We say this is something like the fluorine is internally compensating the electron accepting ability of boron. Right? Suppose you want to go for a party and all the friends are thinking that you will have food in the restaurant, but your mom already feeds you in the home. So you are already internally compensated. Right? You will have less food in the restaurant, right? So that is what is happening over here. So now, so the acidity order will be obviously more donation for fluorine, lesser donation for chlorine, even lesser donation from bromine. So BBr3 will be more Lewis, will be more having more Lewis acidity in comparison to BCl3 in comparison to BF3. Now this question, I can tell you that even CBSE can ask you, or your ICC or Madhyamik, Uच्च Madhyamik can ask you, right? So be careful. Okay, this question comes. Good schools, they will ask you this question. Okay, now, so we have almost discussed most cases. There are a few more backbonding cases. I can stress upon this a little bit more. Now, if I want to, just hold on. Sorry. Where is it? Hmm. All right. So now again, if we have N oxides, now because again over here nitrogen has no accessible d orbitals, this type of back bonding and electron donation is not possible. Okay, but if you compare phosphonium, trialkyl phosphonium oxide, then this type of donation is possible. In fact, the second one is the most stable structure because it is a neutral structure. Okay. Now again, donation of that kind is not possible. But and whenever you have a plus and minus, this type of thing, okay, these are called ylides. Okay, we'll study about this in organic chemistry in some detail. So typically, this is an ylide. Okay. Now here again, the ylide can exist as shown over here. So these are also typical cases of back bonding. So what type of back bonding is happening over here? So we can say this is basically d pi p pi back bonding. Here also it is d pi p pi back bonding. Right. Okay. So this type of back bonding is possible. All right. Now typically you notice one thing that for any type of back bonding to take place, the orbitals should be in the same phase. So that means over here the d orbitals are like this and the p orbital is like that. This type of overlap is taking place. Understood? बोलो. ठीक है ना? Tell me. Okay. All right. So now, having covered all these, we will be discussing molecular orbital theory. So again, why did we need the development of this type of a theory? Now, if you watch the Lewis dot structure of oxygen, you are having lone pairs over here and some bonded pairs, and for bonded pairs, you know, according to VBT, whenever a bond is formed, there is pairing up of electron. Okay. So if all the electrons are paired like this, Ideally, oxygen should have been a diamagnetic molecule, but in reality, oxygen molecule is paramagnetic. What is the proof? So if you have a horseshoe magnet and say this is the North Pole and this is the South Pole, and if you were to you know, put some liquid nitrogen like that, sorry, oxygen, liquid oxygen is blue in color. Now you will see that this type of thin layer would keep sticking with the magnet. This is an indication that oxygen is paramagnetic. Now that does not mean that you take a magnet and you keep running in a field and you think that you will be collecting a lot of oxygen molecules sticking to the magnet. And so I do not know in reality if that would be possible. When you want to purify oxygen, produce pure oxygen, so what you keep doing is you go to a highly oxygenated area and then you have several magnets and you think that all those oxygen will start sticking to the magnet, and that is how you can selectively separate oxygen from the atmosphere. So that is not something that I'm trying to tell you over here. Basically, you have liquid nitrogen that is already in a liquid state, and then if you pour on the magnet, then it will start sticking to it. Okay, and at the same time, if you raise the temperatures, obviously it will be uh, changing its state and becoming gas and going away. But one thing that is sure that liquid oxygen is paramagnetic because it sticks to the north and south pole of a magnet. Bolo. Right. So paramagnetic substances mean substances that have unpaired electrons. Okay. Paramagnetic means has unpaired electron. Okay. Now, so this was the reason that a new type of theory was being developed using quantum mechanical approach. Okay. We will just be using the qualitative things on of this molecular orbital theory, not go into many anything like a theoretical detail or calculation, that type of things, not the mathematics, but just the qualitative approach. What the theory says, what things we can do, and those type of things. Okay, so হ্যাঁ অনেক অনেক ম্যাথমেটিক্যাল ক্যালকুলেশন যেগুলো আমরা করবো না, ঠিক আছে, আমরা জাস্ট ওই ক্রিমটা নিয়ে নেবো. So first thing that we are learning over here is linear combination of atomic orbitals. Okay. So whenever we are combining atomic orbitals, uh, there can be a bonding interaction or a anti-bonding interaction. Okay. So depending on that, we will be getting some new types of wave functions. So those will be bonding wave functions or anti-bonding wave functions. So we will be mostly related or dealing with the picture. Okay. What that wave function looks like, and that is all you have to remember. So first of all, remember when we are combining two separate atomic orbitals, let's call these to be as 1s and 1s of two different hydrogen atoms. Okay, two new set of molecular orbitals will be produced. So the number of atomic orbitals combining will be equal to the number of molecular orbitals produced. So let us think of a situation that we have 1s combining with 1s. When I say plus, that means it is a bonding interaction. When I say minus, that means it is an anti-bonding interaction. Okay. Let's imagine that two waves are combining. So if you have one wave like that, another wave like that, it will give a bigger wave like that. So we say it is a constructive interference. But if one wave is like that and another is like that, so this is the anti-bonding interaction in a very crude sense. That means one is not in phase with the other. So that type of interaction we are saying as anti-bonding interaction. Okay, followed? Okay. So whenever we are having a bonding interaction, so its energy will be lower than that of the atomic orbital. And again, whenever we are having, so if this is the energy axis, let's say, and that is the position of the hydrogen atomic orbitals, whenever they are going a bonding interaction, that means a plus interaction, all right, देखो, yeah. So you will get a wave function that looks like this. ठीक है? Hmm? Okay. Whenever they are having an anti-bonding interaction, in that case, it will be, if this is plus and that is minus, then say this is plus and that would be minus. So this section of the orbital is just a mirror image of the other one. So whenever you have one lobe like this and another one, there is empty space, and another one just the mirror image of the sign, then we say this is having a node. Oh, yes, a node. A node is a point in which there is no electron density. Electron density, the probability of finding electron density is 0 whenever we have a node. And if there is a plane passing through that point, we say that is to be the nodal plane. So this is our nodal plane. So whenever we have to look for a nodal plane, we will check whether if two such orbitals in which there is a gap, or there is some molecular orbital in which there is a gap, and two such lobes are in opposite side. That will be the indication. So this is, we are calling as, if I'm calling this as to be 1s and this has to be 1s, then that is sigma 1s, and for indicating it is anti-bonding, we say it is sigma star 1s. Okay. And another point, so this is some basic things about linear combination of atomic orbitals. We are also calling this as to be LCAO method. Okay. Now, always and always, mentioning of the axis is very much important. So this is z-axis, this should be as x-axis, and that should be as y-axis. So out here, our internuclear axis, okay, as we have defined, is the z-axis. When I say internuclear, what do I mean? a line passing through the nucleus of both the orbitals. So this is the combination of 1s orbital. Let us think of a combination of the 2p orbitals, because there cannot be 1p orbital. Again, we are thinking of a plus combination and a minus combination. This is again a head-on overlap. That means over here sigma will be formed. Okay, sigma bonding orbitals will be formed. So whenever this is suppose interacting in a plus fashion, that means this is minus, this is plus, and this is plus, and this is minus. Okay. So when plus means both pluses are combining with each other. So over here we should be getting a bigger plus like this. These are the nucleus, and a small one like that. Now you can ask me, sir, how these things pictures are coming. My simple answer to you over here is that these are all new wave functions generated using mathematics, and their plot would be like that. So we are not dealing with that mathematics. You just need to remember the pictures. Okay. Now if you say, sir, what if it is undergoing a anti-bonding interaction? Okay. So then again we will say that is the picture. I think I might have got the S anti-bonding orbital wrong. Okay. Wait. So this is plus and that is minus, and that is plus and that is minus. Okay. So this guy would be having a nodal plane. So over here, this is again, suppose these are two p z orbitals. So this is basically sigma 2pz, and that is sigma star 2pz. Understood? Okay. বুঝতে পেরেছিস তো? Any questions so far? Guys, কি রে আওয়াজ যাচ্ছে না যাচ্ছে না? So this is head on, okay? Overlap. And we are calling this to be as bonding and that to be as anti-bonding. Okay. Another interesting part, this dotted line we are calling this to be as the barycenter. So whenever you have an orbital lower in energy than the atomic orbital, these are your atomic orbitals, which we are calling as AO. Then those are bonding orbitals. Whenever it is raised by an equal height, then we are calling those MOs. So these are your molecular orbitals. So this guy is the bonding and that guy is the anti-bonding. Am I clear up till here? Dipro আবার আওয়াজ আসছে না. Anshu. Guys. ठीक है. So I'm moving forward. Okay, so we are not having this one correction over here. We are not having this chota wala putki. Okay, so just this. Okay, yeah, yeah. Uh, okay, fine. Hmm. Hmm. Okay, now you see we have two sets of p orbitals now. One is 2px, another is also 2px, or else we can have 2py and 2py, right? So those are undergoing side-on overlap, and that can again be a bonding, and the above one is anti-bonding. So this is bonding and that is anti-bonding. Okay. So the pictures now we are going to get are going to be as follows. Now again what you can see over here is that this top sign and the below sign, they are different. So obviously there is a nodal plane passing through the internuclear axis. Okay. So this is a question that is asked. In a side-on overlap of p orbitals, how does the nodal plane pass? Again, for the anti one, so this is plus and that is plus and that is minus and that is minus. Okay. स्क्रीन शेयर नहीं है. Wait. And there would be another one like this and like that. So now this is plus, this will be minus. If that is minus, this will be plus. Okay. Now what you can notice over here, this is the nucleus and that is the nucleus. If you make a line or pass a line through the internuclear axis, then also the top part and the below part are mirror images of each other. And if you pass a line like this, which is perpendicular to the internuclear axis, then also they are mirror images of each other. So this guy or this lone pair MO diagram is having two nodal planes. Okay. So this is the only question that you can expect regarding these type of diagrams. Okay. So this is now called pi 2px, and that is called pi star 2px. So similarly, we can have another set of orbitals of same energy when 2py and 2py combine. That would be pi 2py and pi star 2py. Okay. So these things you keep in mind. Now, I've already a few things which I'm again repeating. The number of AOs combining is equal to the number of MOs forming. Okay. In 3, we will say the molecular or MOs are arranged in the increasing order of energy. Okay. The electrons are filled in MOs following Pauli's exclusion principle. And Horn's rule of maximum multiplicity. পাউলি কি বলেছে, দুটোর বেশি ইলেকট্রন তুমি একটা অ্যাটমিক অরবিটালে ভরতে পারবে না। সিমিলারলি ফর এ এম one molecular orbital means maximum capacity 2 electrons. Horn's রুলটা কি? ডিজেনারেট মলিকুলার অরবিটালস থাকলে আগে তুমি আনপেয়ার করে ফিল আপ করবে, তারপরে যখন সব কটাকে আনপেয়ার্ড ইলেকট্রন দিয়ে দিয়েছো তারপরে আবার পেয়ার আপ করতে শুরু করো ইফ ইউ হ্যাভ এনি এক্সেস অ্যামাউন্ট অফ ইলেকট্রনস। ওকে, তো এই রুলগুলো আমরা ফলো করব, দিয়ে এমো ডায়াগ্রামসগুলো আমরা লিখব। তাহলে মলিকুলার অরবিটাল ডায়াগ্রাম, এটাই তোদের বোর্ডসে বা কম্পিটিটিভে বেশি করে আসবে ফর H2। দেখা যাক কি হয়। তো প্রথম কাজটা হলো কি, যে দুটো এরম ড্যাশ লিখবি, তার মানে হচ্ছে গিয়ে এটা হচ্ছে আমার এনার্জি অ্যাক্সিস, সেটাতে তুই ই লিখবি, একে 1s বলবি, একেও 1s বলবি। মানে এখানে একটা হাইড্রোজেন অ্যাটম আছে, এখানে একটা হাইড্রোজেন অ্যাটম আছে, দিয়ে তলায় HAO HAO এটা লিখে দেওয়া মানে হাইড্রোজেন অ্যাটমিক অরবিটাল আমি বলতে চাইছি, এবং দুজনেরই একই এনার্জি। এবার এই দুজন যখন কম্বাইন করছে, দুজন দুজনকে যখন অ্যাপ্রোচ করছে, করার পরে যখন তারা আলটিমেটলি ওভারল্যাপ করলো, তখন একটা ইন্টারাকশন বন্ডিং হবে, আরেকটা অ্যান্টি বন্ডিং হবে। তাহলে এই ডটেড লাইনটা ইন্ডিকেট করছে যে এই দুটো অরবিটাল ইনভলভড হয়ে এই দুটো নতুন এনার্জি লেভেলস তৈরি হলো, যাদেরকে আমরা মলিকুলার অরবিটালস অফ H2 বলে জানবো। তাহলে এটা হলো গিয়ে সিগমা 1s মলিকুলার অরবিটাল অফ H2, আর এটা হলো গিয়ে সিগমা স্টার 1s। তাহলে হাইড্রোজেনে তো একটা করে ইলেকট্রন, তাই না? তাহলে আগে লোয়ার লেভেলটাকে ফিল আপ করবো, তো সেই জন্য পাউলির প্রিন্সিপাল ইউজ করে আমরা ফিল আপ করে দিলাম। ওপরটা লেখা থাকবে কারণ আর তো ইলেকট্রন নেই। তাহলে যদি তুমি এবার বন্ড অর্ডার লিখতে চাও, মানে one way of finding bond strength, number of bonding electron minus number of anti bonding electron। তো বন্ডিং ইলেকট্রন কটা? দুটো। অ্যান্টি বন্ডিং ইলেকট্রন আমার কাছে নেই, তাহলে আমি বলবো 1। ইন রিয়ালিটি হাইড্রোজেনের মধ্যে একটাই বন্ড থাকে। কি বোঝা গেল? আচ্ছা, তো এবার বলবে কি, তোমাকে বলবে এটা কি ডায়াম্যাগনেটিক স্পিসিস, তুমি বলবে হ্যাঁ। ডায়াম্যাগনেটিক। আচ্ছা, এতে তাহলে মিউএস ভ্যালুটা কি? ভাই মিউএস মানে কি? n+2 বোর ম্যাগনেটন। তো n এর ভ্যালু তো এখানে 0, তাহলে 0, মানে যে কোনো ডায়াম্যাগনেটিক কম্পাউন্ড হচ্ছে মিউএস ভ্যালু মানে স্পিন অনলি ম্যাগনেটিক মোমেন্টে কিন্তু 0, বিকজ n is 0। আচ্ছা, আর কি